Hello, in this video we study linear transformations. During the course I mentioned several times that a matrix can be considered as a linear transformations, and when we study matrix multiplication I also provide several examples on how we can consider matrix multiplication as superpositions of linear transformations. In this chapter we study details about that. Okay, look at this picture. Suppose that we have matrix A of the size m by n, means A has m rows and n columns. So if you want to apply matrix A to some vector x, then you get a vector ax in here. So what is the size of the vector x? The size of the vector x should be n times 1, right? Because here you have m by n. That means, x has n coordinates. At the end, by the matrix multiplication, the vector ax has the size m by 1. Means ax is a vector in Rm, right? And x should be a vector in Rn. So look at this. We may consider A as a map from Rn to Rm. Make sense? And of course, this map is linear. Why? This map is linear because, A lambda x is just equal to lambda ax. And A x plus y equal to ax plus ay. We have these two properties because of matrix multiplications, right? So from that point of view, A is a linear map. A is a linear map. So that's why we can consider a matrix as a linear map. And we call such linear maps linear transformations. Make sense? Because we transform one vector x into another one. That's why, we have transformation. Okay? In this situation, we have different spaces, Rn and Rm. So if you consider Rn and Rn means the matrix A is square. So you have a linear transformation in the same space. Let me show you one picture. This is a program Photoshop online. All right? I have picture right here. I want to change the photo like this. I'm doing some linear transformation. Make sense? So in this case, so we fix the point in the corner on the right hand side, right? And then we change the point on the left hand side. So we just change the coordinate of that point with respect to the other corner, with respect to the fixed one. Or, in this case, we can consider that fixed point as the origin. You may consider maps. You can find matrices that change such coordinate. Not only this, most of motions can be considered as a linear transformation. Of course, the situation is more complicated, right? It depends on, how you describe the motion, but, you may consider. Let's consider the following example. You have map T from R2 to R2 such that T x y equal to x minus y, x plus 2y. First, this is a linear transformation. Why? Because that map satisfied these two properties. Okay, so we can check that easily. Suppose we have two vectors x and y. You need to show that A lambda x plus y is equal to lambda ax plus ay. right? And you can suppose that x is just x1, x2, and y is y1, y2. There are two vectors. So you plug x1, x2 into this formula to check. I have lambda, a lambda, x1 plus, not x1 plus x2r. I have a lambda x1 plus y1, and here lambda x2 plus y2, because I just add two vectors in here. And by the definition of this linear transformation, I have that is lambda x1 plus y1 minus lambda x2 plus y2. That is the first coordinate, right? The second one is x plus 2y. So I have lambda x1 plus y1 plus 2 lambda x2 plus y2. Oh, I want to get the form lambda ax plus ay. I need to collect all terms with lambda, okay? So I have lambda x1 minus lambda x2 in here. And then plus y1 minus y2. The second one is lambda x1 plus 2 lambda x2 plus y1 plus y2. And then we break this into sum of two vectors, lambda x1 minus x2 lambda x1 plus 2x2. Another one is y1 minus y2, y1 plus 2y2. I think we have two in here. I mixed two right here. Okay, and this is lambda x1 minus x2, x1 plus 2x2 plus y1 minus y2, y1 plus 2y2. But what's this? This is just ax, and this guy is ay. So basically, T is a linear transformation. All right. Now, once we have linear transformation, we can find image of a vector via this linear transformation. So like, let's find the image of V. -1 and 2. So you just need to plug V into the formula. You have TV equal to x is -1 minus y is 2. X plus 2y, 2 times 2, which is -3 and then 3. Is it? If they ask you to find the pre-image of some vector, you might do that too. Find the pre-image of W equal to -1 and then 11. What does it mean? That means, if you have a point right here, right? For example, via T, you can find TV. And now you apply the inverse. You have W in here. They ask you to find the pre-image of W. So that means you just need to find, the guy who was transferred to W via T. So you might think about, T to -1, right? But right now, we don't have right to apply T to -1. Makes sense? We do that in another way. So that means I need to find the guy V1, V2 such that T V1, V2 is equal to W. Makes sense? So I have the following one. V1, V2 and T V1, V2 is what? T V1, V2 is V1 minus V2. And here we have V1 plus 2V2. And this is equal to W. W is -1, 11. So basically, if you compare coordinates of these two vectors, right? So you get this guy equal to -1 and V1 plus 2V2 equal to 11. You have a system of linear equation. V1 minus V2 equal to -1 and v1 plus 2v2 equal to 11. If you write this in the matrix form, you would have the following: 1, negative 1, negative 1, 1, 2, and 11. Right? So basically, in order to find pre-image, you need to solve this system. Look at this. This system is A, V equal to W, where W is negative 1, 11. A is the matrix 1, negative 1, 1, 2, and V is V1, V2. So solving this, that means you solve for V, and suppose that the matrix is invertible, right? So you have pre-image. So basically, you need to solve the system linear equation. You see? But we can check that the matrix is invertible, right? In this situation. Not always, but in this situation. Because the determinant of that matrix is what? Because that of A is equal to 2 minus negative 1 is 3. Not 0. The matrix is invertible. So vector W has pre-image. But as we learn from the topics of system linear equations, not every system has solution. They give you a system, we might have three cases. The first case, the system has no solution. The system has infinitely many solutions, and the system has only one solution. In this case, the system has only one solution, which is good. But in many cases, you still have other two situations: no solution or infinitely many solutions. Don't forget about that. Okay? It really depends on the definition of the linear transformations. Okay? But you know, from this example, we learn one thing. Look at this. Look at the matrix A and the T, the map T. The coefficient of the matrix is 1, negative 1. They are coefficients of the first coordinate right here, 1 and negative 1. This is 1, this is negative 1, right? The second row of the matrix A is 1 and 2. They are right here, 1 and 2. So basically, for this linear transformation, you can make a matrix which is corresponding to T, right? And you might have the following identity. TV is equal to AV. Is that correct? TV is equal to AV. Or, you know, if we write that strictly and correctly, you have the following one. Yeah, TV, the transpose. Or TV is equal to AV transpose. Right? You can look at this, the definition. So we need transpose because, you know, in this case, we have negative 1, 11, and here is negative 1, 11. That is just transpose, right? Okay? So this example just tells you that for the linear transformation T, you have a corresponding matrix A such that TV transpose equal to AV or TV equal to AV transpose. Okay? And it turns out that this is true for any linear transformation. Okay? This is true for any linear transformation. That means, you know, for any linear transformation, there is a matrix A such that you have these properties. Suppose you have f of x equal to psi x. Of course, this is not linear. Why? Because psi of x and y is not psi of x plus psi of y. Right? And parabola, that is not linear. We know that. The linear case is only ax plus b. Right? So, you know, That is really important. Okay. Uh, Given that we have only linear functions in here, but actually they are really important. Let's consider properties of linear transformation. We have t negative v. It should be negative tv. The second one, t of 0 should be 0. This is obvious because t is linear. The next one, you have tv minus u. That is tv minus tu. Okay? And the last one, t sum of lambda I vi. That is just lambda I sum t vi. You know, all these properties are trivial. If you look at linear transformations from the point of view of matrices, so you can see all these properties from properties of matrix multiplications. Makes sense? So you have a negative v equal to negative av. You have a of 0 is just 0. You have a of v minus u is just av minus au. And a of sum of lambda I vi, that is just sum of lambda I a vi. All these properties from matrix multiplications. There's nothing special. Make sense? All right. Now, in the very first example, they give us the formula of linear transformation. They ask us to find image of vectors. That's good. If you have a vector, you just plug coordinates into the formula of t to find image. But now, in many cases, we don't have that. But suppose you do experiments, right? And you each time you measure, it turns out that you can find image of vectors, right? You know image of vectors. And they ask you to find the form of linear transformations. How about that? Or you may know the image of some vectors, and they ask you to find image of another vectors based on the information you know. All right? So let's solve such a problem. Example. We have T is a linear transformation from R3 to R3 such that T of 1, 0, 0 is 2, negative 1, and 4. T of 0, 1, 0 is 1, 5, and negative 2. And T of 0, 0, 1 is 0, 3, and 1. They ask you to find T of 2, 3, and negative 2. So if you look at this picture, we have R3 in here. Okay, here's R3. You have 3 points, so you have image of 3 points or 3 vectors, right? You know this guy, this guy, this guy, and they give you another point right here. They ask you to find the image of this. So that is the whole picture. You know, in many cases, we can solve such problem easily. Okay, so how? We'll use this property. We use this property from the linearity of T. So basically, if you have some Vi, right? You know image of Vi, right? And you have some vector, suppose, you know, x0 or v0, whatever you want. You express x0 as a linear combination of Vi, right? That means you can find lambda I. Once you have lambda I right here, you have T, Vi right here. You can consider the linear transformation of those images. And then you can find the image of x0. Make sense? For this problem, yeah, it's pretty easy because these three vectors are vectors in the standard basics of R3. Make sense? So I have 2, 3, -2 is 2, 1, 0, 0 plus 3, 0, 1, 0 minus 2, 0, 0, 1. From here, I apply t to both sides. I get t 2, 3, -2 equal to 2t 1, 0, 0 plus 3t 0, 1, 0 minus 2t 0, 0, 1. And we already know image of vectors in the standard basics. This is just 2 times 2, -1 and 4 plus 3 times 1, 5, -2 minus 2 times 0, 3 and 1. Let's sum them up. We get the answer of the problem. So I have 2 with 2. Okay, 2 times 2 plus 3 times 1 minus 2 times 0. That is the first coordinate. The second one is -2 plus 15 minus 6. The last one is 8 minus 6 minus 2. So overall you get 4, 3 is 7. Here 7, 8. And here, no, we have 7 right here. And 0. And that is the image of 2, 3, and -2. From this example, we may generalize it. We may use this technique, this idea for any problems like this. Make sense? Even they don't give you 1, 0, 0, 0, 1, 0, 0, 0, 1. Whatever they pick. The only thing you need to do is you have to express your vector right here as a linear combination of those vectors right here, right? And then apply t to the whole linear combinations. And of course, sometimes you cannot express this vector as a linear combination of the given one. In that situation, the problem is unsolvable. Make sense? So that means we don't have enough information to determine the image of this vector. And now, let's look at this problem from point of view of matrices. The first step I need to do is I express vector 2, 3, -2 as a linear combination of previous vector. So I write those vectors in the column form. Right? Once I solve this, I just need to apply the image of what? Of those vectors to the solutions of this system, right? The image of this is 2, -1, 4. I write them in the column form. 1, 5, -2, 0, 3, 1. And I apply to 2, 3, -2. And I get exactly 7, 7, and 0. Make sense? So, we can solve such problem using matrix forms. That is interesting. Look at this. That is the first vector v1, the second vector v2, the third vector v3, and that is v0. You have image of v1, v2, v3. They are right here. tv1, tv2, tv3. And they ask you to find tv0. You see that? And this is nothing but the coefficients of the linear the linear combinations. That means the solution of this system. Look at this. Make sense? All right, let's consider the following example. First one is rotation in R2. Let's show that A cosine theta, negative sine theta, and cosine theta has the property that it rotates every vector in R2 counterclockwise about the origin through the angle theta. Realize the rotation. Okay, so the rotation looks like this. You have some point here. Okay, if you look at the circle, so if you are right here, this is your vector. You apply this vector. You apply the matrix A to this vector. You just rotate this vector, right, on the angle theta. Agree? So let's show that. Of course, A is the linear transformation because, you know, A is a matrix, right? We just discussed in the very beginning of the lecture. So we know that it's a linear transformation. Okay. So if you have, suppose you have the coordinate x, y right here. So and the radius is r. We have polar coordinates x equal to r cosine of phi, and then y is r sine of phi, where phi is the angle between this vector n and the x-axis right here. Okay, now let's apply A to xy. So you have ax equal to cosine theta minus sine theta, cosine theta, applied to r cosine phi, r sine phi. Let's multiply them. We get, okay, I write in here. Since r is just a number, we can take that out, right? We can take r out. Inside you have cosine theta, cosine phi minus sine theta, sine phi. The second coordinate is sine theta, cosine phi, plus cosine phi, cosine theta, sine phi. So basically, what's that? That is r. In the first coordinate, cosine minus sine, that is cosine of sum, right? So I have cosine of theta plus phi. You have sine, cosine plus cosine sine. So that is nothing but, you know, sine of what? Theta plus phi. So basically, you just change r cosine phi, r sine phi equal to r cosine plus phi, r sine theta plus phi. So that is rotation. Orthogonal projection. That's what we learn in chapter of inner product spaces. It also can be considered as a linear transformation. Let's consider the following example. You have map T from R3 to R3 such that the AT equal to 1, 0, 0, 0, 1, 0, and 0, 0, 0. The AT is the matrix corresponding to T. Okay, so if you apply AT to some vector x, y, and z, or some point x, y, and z, you have 1, 0, 0, 0, 1, 0, 0, 0, 0, x, y, z. And that is just x, y, and 0. So basically, you project the point x, y, z onto the x or y plane, right? Because, you know, the z coordinate of the image is just 0. That is the point on the x or y plane. Make sense? In the case, if you want to project some point onto some subspace, you might consider similar thing like that. Agree? We have another geometrical examples like this. Suppose you have x or y plane and you want to consider symmetry. This is xy and you want to consider symmetry with respect to the x-axis. So the new coordinate in this case is what? Is x negative y. How to find the matrix that realize this transformation? So basically you have t, x and y equal to x negative y. You want to find matrix A of t, right? So you write ATXY equal to x negative y. Makes sense? So basically, you can write in the following way. X plus 0y. And then 0x minus y. From this form, you can see the coefficients of x and y in this vector. And now you can guess the matrix AT actually is equal to 1, 0, 0, and negative 1. Let's verify this. You multiply this matrix with the x and y, you get 1, 0, 0, negative 1, x, y. In the answer, you have x and negative y. You see, that's what we have right here. So this example shows you how to get a matrix from the form of linear transformation. Actually, we already did this in the very first example. All right? So let's consider another example in calculus. That is differential operator. Differential operator. You consider the vector space C1 AB. That is the space of all functions whose derivatives are continuous on AB. Or we can say that is the space of differentiable functions. Okay? Let's show that the differential operator D operator dx is a linear transformation. So we have dxf. What's that? That's d dxf, right? Or that is just derivative of f. Okay, it's just derivative of f. We need to show that dx lambda f plus g equal to lambda dxf plus dxg, where lambda is some scalar and g is a function in C1AB. But that is obvious. That is from the properties of differentiation rules, right? Derivative of sum is just equal to sum of derivative. And this property is also trivial. So that means the differential operator is a linear transformation. Okay? Here's homework for extra credit. Get the matrix of dx. Please send me your answer. All right? You might consider integration. Definite integral is a linear transformation too. Definite integral is a linear transformation. So you consider map T from P to P, where P is the set of polynomials. Such that Tp small is equal to definite integral of Px dx. Okay. No, I would write without AB. Let's say that, because we consider maps from P to P. So antiderivative of a polynomial is a polynomial. Does it make sense? Again, from properties of integrals, you can see that actually T lambda P plus Q equal to lambda TP plus TQ. That's it. So this is a linear transformation. All right, so again, this challenge, again, you may consider the matrix of T. All right, so I think we finished this section right here, and we have a couple of homework problems. I hope that you can solve and then send them to me. Thank you, and see you in the next video.